In this video, we are going to evaluate integrals using trig substitution. It is important to understand the nature of the trig equation and its associated triangle. So let us discuss these concepts before we begin. We know that tangent of an angle is equal to the side opposite of the given angle over the adjacent side of the angle. So setting up my triangle, here is my angle theta, and opposite of that angle theta is x, and adjacent to the angle theta is a. So now all I want to do is solve for the missing side, and we do that using Pythagorean theorem. So we have that a squared plus x squared is equal to, how about we let the missing side be called b? So that's going to be a squared plus x squared is equal to b squared. And I want to solve for the missing side. So I will take the square root of both sides. So b is equal to the square root of a squared plus x squared. So I'm going to fill that in. So here, this is equal to the square root of a squared plus x squared. The side that we just solved for is similar to the way your question will be presented to you, and it gives you a clue on which trig equation and triangle to use. Next, we discuss how to prepare our trig equations for substitution. The first thing you're going to do is you're going to find x and dx. So, first thing we're going to do is find x and dx. So we have that tangent of theta is equal to x over a. So tangent of theta is equal to x over a. And if I solve for x, then x is equal to a tan theta. Now if I find dx, then dx is just going to equal to a secant squared theta d theta, because the derivative of tangent is secant squared. Now what we want to do is we want to find theta and its range. So we're going to find theta and its range. So again, we know that tan of theta is equal to x over a. Now if I take tan inverse of both sides, then we have tan inverse of tan of theta is equal to tan inverse of x over a. So this allows us to undo the tangent function. So we just get theta on the left-hand side. So theta is equal to tan inverse of x over a. Now, to find the range, you want to understand the graph of inverse tangent. So the graph of inverse tangent looks something like this. So we have a horizontal asymptote at negative pi over 2, and we have a horizontal asymptote at pi over 2. And inverse tangent is going to swing out like this. So we see that the domain of inverse tangent goes from negative infinity to positive infinity, and the range of inverse tangent goes from negative pi over 2 to pi over 2. So that means that the range of theta has to be between the interval negative pi over 2 to pi over 2. So we say that theta belongs to the interval between negative pi over 2 to pi over 2, and not actually including negative pi over 2 and pi over 2, which is why we have parentheses and not brackets. And we're not including negative pi over 2 or pi over 2 because we have horizontal asymptotes, so the graph does not actually touch pi over 2 or negative pi over 2. So what this essentially means is that when you pick your values for theta, here's negative pi over 2 and here's pi over 2. Your values for theta has to come from this right region of the unit circle, but not actually including negative pi over 2 or pi over 2. Next, we discuss how to actually apply trig substitution and how to rewrite the integrand to make integration easier. So we begin with the side that we solved for, because that is the part of the question that will be given to you in the problem. So the part of the question that you are given, that is the part that you want to rewrite. So we see that x is equal to a tan theta, so I'm just going to substitute x for a tan theta. So this is going to be equal to a squared plus a tan theta squared. And now I'm just going to rewrite this and say that this is equal to a squared plus a squared tan squared theta. And now I'm going to factor out an a squared, so this is equal to a squared times 1 plus tan squared theta. So that becomes a times the square root of 1 plus tan squared theta. And we know by the Pythagorean identity that 1 plus tan squared theta is equal to secant squared theta. So this is equal to a times the square root of secant squared theta. So, which means that this is equal to a times the absolute value of secant theta. Now, we know that the angle theta is between negative pi over 2 to pi over 2. And we know that secant of theta is just 1 over cosine theta. And cosine theta takes on the x values, and we know that sine theta takes on the y values of the unit circle. So that means that this right region will only have positive x values, okay? Which means that secant theta will always be positive in this interval between negative pi over 2 to pi over 2. So we can say that this is equal to a secant theta, since theta belongs to the interval between negative pi over 2 to pi over 2. Then secant of theta is always greater than 0, which implies that the absolute value of secant theta is equal to secant theta. Thus, we know that the square root of a squared plus x squared is equal to A secant theta. Now that you have the background for trig substitution, we are ready to work an example. Let us look at our first example. I kept everything on the board that I will use for reference. After I work this problem, I will show you a shortcut for how to work the problem, so be sure to stick around until the very end. Here we have the integral of 1 over the square root of 9 plus x squared dx. And we're going to evaluate this integral using trig substitution. So the first thing we're going to do is we're going to identify the trig equation and its associated triangle. We see that this integral is in the form 1 over the square root of 3 squared plus x squared dx. And clearly it matches the side of the triangle that we solved for. So if I were to write the tangent equation and its associated triangle in relation to this problem, it would look like this. So we have tan of theta is equal to x over 3. And when I draw my triangle, it will look like this. Okay, so we have x here, and we have 3 here, and we have the square root of 9 plus x squared. And if I want to go ahead and just use this equation here, that is going to be the square root of 9 plus x squared is equal to 3 secant theta. This equation will be useful for later when I show you the shortcut. Next, what we're going to do is we're going to find x and dx. So we're going to find x and dx. So we are given tan of theta is equal to x over 3. So I'm going to write that. Tan of theta is equal to x over 3. And if I solve for x, we get that x is equal to 3 tan of theta, which means that dx is equal to 3 secant squared theta d theta. And now I want to find theta and its range. So find theta and its range. So again, starting with my equation, tan of theta is equal to x over 3, and taking the inverse tan of both sides, we get that theta is equal to tan inverse of x over 3. And the range is between negative pi over 2 to pi over 2. So we say that theta belongs to the integral between negative pi over 2 and pi over 2. So that is the range of theta. Next, we are going to apply our trig substitution. So beginning with what we started with, we have the integral of 1 over the square root of 9 plus x squared dx, and that is equal to the integral of 1 over the square root of 9 plus, now I'm going to substitute 3 tan theta for x, so that's going to be 3 tan theta squared, and I'm also going to substitute 3 secant squared theta d theta for dx. So that's times 3 secant squared theta d theta. Now I'm going to just rewrite 3 tan theta squared. So this is equal to the integral of, I'll write the numerator first, 3 secant squared theta d theta divided by the square root of 9 plus 9 tan squared theta. And now I'm going to factor out a 9. So we have integral 3 secant squared theta d theta divided by the square root of 9 times 1 plus tan squared theta. Notice that I am following the same procedures as I did in the very beginning of this video. So now I'm going to pull out the 9 here. So we're pulling out the 9 from up under the square root. So this is equal to the integral of 3 secant squared theta d theta divided by 3 times the square root of 1 plus tan squared theta. And now we get a cancellation here. So that's secant squared theta d theta divided by the square root of, now 1 plus tan squared theta is equal to secant squared theta. So this is equal to secant squared theta. So this is equal to the integral of secant squared theta d theta divided by the absolute value of secant theta. And we know that since theta belongs to the interval between negative pi over 2 to pi over 2, that secant of theta is always positive. So we can say that this is equal to the integral of secant squared theta d theta divided by secant theta. And we say this because since theta belongs to negative pi over 2 to pi over 2, this interval here, then the absolute value of secant theta is equal to secant theta, because secant theta is always positive in this interval. So now I can cancel the numerator and the denominator. So this is going to give me the integral of secant theta d theta. Now I need to apply a little trick to finish integrating this problem. What I'm going to do is I'm going to multiply the numerator and the denominator of this integrand by tan theta plus secant theta. So applying this, we have that all of that is equal to the integral of secant theta times tan theta plus secant theta divided by tan theta plus secant theta d theta. Now I'm just going to multiply secant theta across the parentheses. So this is equal to the integral of secant theta tan theta plus secant squared theta divided by tan theta plus secant theta and d theta on the outside. Now what I'm going to do is I'm going to apply U substitution. So we're going to let U equal tan theta plus secant theta. Then du is equal to secant squared theta plus secant theta tan theta d theta. And now I'm going to solve for d theta. So this implies that d theta is equal to 1 over secant squared theta plus secant theta tan theta du. So just to recap this, I let u equal the denominator. Then when I took the derivative of tan theta is secant squared theta, and the derivative of secant theta is secant theta tan theta. Then I solved for d theta. So to solve for d theta, I need to divide both sides of the equation by secant squared theta plus secant theta tan theta. And that will get d theta by itself. And we will have 1 over secant squared theta plus secant theta tan theta du on the other side. And I just sort of rewrote the right side of the equation on the left and the left side of the equation on the right. I just restructured it that way. So now I can simply substitute d theta for 1 over secant squared theta plus secant theta tan theta du, and I can replace tan theta plus secant theta with u. So that's what I'm going to do. So we have that this is equal to the integral of secant theta tan theta plus secant squared theta divided by u, and that's multiplied by 1 over, we're substituting d theta in, so that's 1 over secant squared theta plus secant theta tan theta du. And notice we get a cancellation. We have secant squared theta plus secant theta tan theta in the numerator, and we have secant squared theta plus secant theta tan theta in the denominator, so they can cancel. So now we have that this is equal to the integral of 1 over u du. Now this is very easy to integrate, so the integral of 1 over u du is just the ln of the absolute value of u plus c. So this is equal to ln of the absolute value of u plus c. And now what we want to do is we want to plug back in the value of u. So we let u is equal to tan theta plus secant theta. So this is equal to the ln of tan theta plus secant theta plus c. And last, what we want to do is we want to rewrite our answer in terms of x and not theta. So I need to rewrite tan theta as x over 3. So this is equal to ln of the absolute value of x over 3. And I want to write secant theta in terms of x as well. So coming to my triangle, I know that secant of theta takes on the value hypotenuse over adjacent. So the hypotenuse is the square root of 9 plus x squared, and adjacent is 3. So I can rewrite this as the square root of 9 plus x squared over 3 plus c. And that is your final answer. Now let us talk about that shortcut I was telling you about. Notice this equation right here. So if you're given a problem and part of that problem has the square root of a squared plus x squared, you can use this equation to skip a lot of steps. So for example, if I started here, if I say the integral of 1 over the square root of 9 plus x squared dx, Now, if I go ahead and substitute dx for 3 secant squared theta d theta, and if I substitute the square root of 9 plus x squared for 3 secant theta, then I can rewrite this as the integral of 1 over substituting the square root of 9 plus x squared as 3 secant theta. So that's going to be 3 secant theta. And substituting dx for 3 secant squared theta d theta. So that's 3 secant squared theta d theta. So that gives me the integral of secant theta d theta. And notice that is the step here. Look how many steps you could have skipped. So once you get here, you can just finish the problem like you did before. Now be careful, because if you're given the problem where it's just 9 plus x squared and it's not under a square root, then you would need to manipulate this equation. So you would need to square both sides to get 9 plus x squared is equal to 3 secant theta squared. And that is how you evaluate integrals using trig substitution. Thank you for watching, and I will see you in the next video.